So I hope you had a nice lunch. And we're really excited to start again the conversation that we left with Mario earlier today. So this session is called Programming the Physical World. So I just wanted to introduce briefly the topic. Basically, this is a quote, actually, from an interview from Professor Neil Gershenfeld, interviewed by CNN a couple years ago. For those who don't know, Gershenfeld is the founder of the Center for Bits and Atoms at MIT, and has been like mostly at the forefront of the sort of discourses on fab labs and the way they can empower people through tools of digital fabrication. And basically he was saying, quote, "What's emerging now is a science of digital fabrication that lets you turn data into things so we can program the physical world." So beyond just digital fabrication, I really was interested into that quote because there's this idea that we're almost in a sort of a science fiction terminology where we're entering territories of the Matrix or, you know, X-Men and so on, where we're sort of imagining that with our data, our thoughts, our emotions that can be tracked and transformed into numbers, we can then feed that back into the tangible artifacts around us. So the topics we're going to see today is really trying to sort of have a very brief overview of those possibilities through speculative design and imagining what is really possible in the near future and actually already happening, and with also beyond that the math that are at the root of that sort of visualization and the way we can represent geometry that can then be touched or used in space. Yes, that's about what I wanted to say on the topic. I'm just going to first introduce the first talk by Jessica Rosenkrantz. Here, her talk is called Growing Objects. She's going to mainly address generative techniques, 3D printing and interactivity through also the company that she co-founded in 2007, Nervous Systems. And I think she's going to also mention some of her inspiration in biology and natural pattern formation. Jessica is really at the intersection of art, science, and nature in that way. She likes to play with natural processes that generate pattern and form. I really like a quote that she was mentioned, like in an interview with her business partner, Nervous System, where they were like saying that they got together because they shared an interest in creating tools to generate architecture. But we soon, quote, realized that we'd never actually see these buildings being made, so we decided to make products that people could have. So mentioning the jewelry that they're starting off with Nervous System, but now they're also leading into geometry and architecture that you can wear with a 4D printed dress. I'm just going to let her talk and have our first talk. Yes, thank you.
The secret button. Okay, well, this is an interesting experience for me. I've told a number of random people I've met today that actually the last time I think I was at the GSD was the day that I dropped out. I'm not an academic and I'm not an architect. In fact, I am a sort of commercial product designer. So I'm sort of perhaps coming at this from a different perspective that I'm going to tell you about today. I think this probably advances my slides. Yes. Okay, so that's me and my partner, Jessie. And we founded our company Nervous System in 2007 when we were both still students. The idea behind the company was to sort of create a place where we could do cross-disciplinary experiments, sort of be a creative outlet for things that didn't seem to fit into the structure of our educations. His background is in math and computer science, and I have a background in biology and architecture. And we wanted to create a place where we could combine all those things together and see what comes out. Our projects really focus on three main areas of interest. We're interested in science and nature, so understanding the processes by which the shapes and patterns we see in nature form. That interest embraces diverse phenomena like biological, chemical, physical, geological, and even social processes. We're also fascinated by digital fabrication, so how can new computer-controlled manufacturing techniques make possible new types of design? How can they influence the way we construct the world around us and even express ourselves? And the last thing we're really interested in is this idea called co-creation, so combining together our interest in algorithms and our interest in fabrication. How can we create new types of design tools that are more powerful, accessible, and even democratic? Okay, now we have the quote, because all architecture talks need to have a quote in them. We might call the form of an organism an event in space-time and not merely a configuration in space. I really like this quote by Darcy Wentworth Thompson, which was probably written about 100 years ago, because it identifies the way in which all the forms we see in nature are the result of complex dynamic processes. These processes grow and adapt to different conditions, and the resultant forms that we see are expressions of the processes and the conditions that generated them. I see this idea of form as process as an interesting counterpoint to how humans have traditionally constructed objects. Humans tend to take or all of us in this room probably, tend to take a very top-down approach to design. We design objects by directly specifying maybe precise measurements and shapes. We essentially almost determine the final shape of whatever we're designing at the very outset of a project. Computers are often advertised as offering new ways of making, but in fact, most design software just merely tries to mimic or reproduce methods by which we've made things before computers. We have software that gives the experience of drafting, sculpting, model making, and even things like shipbuilding. And they translate how we've worked traditionally with materials like paper, wood, clay, and metal into some sort of strange digital version of those experiences. At Nervous System, we're interested in trying things in a different direction. We take inspiration from nature's process-based designs and focus on developing interactive processes that we can engage with. So instead of creating static designs, we create dynamic systems, and instead of drawing structures, we're interested in growing them. We also, as I mentioned, have a strong interest in digital fabrication. Computer-controlled manufacturing techniques like laser cutting and 3D printing and water jet and all these things, they open up new possibilities for making, which we heard about in the earlier session. They enable us to make incredibly complex objects, to make one-of-a-kind objects, cheaply and easily, more cheaply and easily than you could ever do before with mass manufacturing. And in fact, they lower the barrier to creation. 3D printers, for instance, are becoming cheaper and cheaper, and they're sort of proliferating into every aspect of our lives, in our offices, libraries, and even our own homes. However, everything I just told you is a little bit of a lie. That's the dream, right? The reality is that there's a key part of the problem missing, right? Software. How do you design the stuff you want to make with these machines? The machines are very powerful. The complexity is free and variation is free. I told you all these things, and lowers barriers to creation, but design software is hard to use, very expensive. It isn't designed with complexity in mind. It's hard to generate complex structures. And in fact, it's also hard to make variations on things. This idea of variation is not embedded in how we create things. So part of what we're doing in Nervous System is try to think about how can we create new types of design experiences and tools that leverage what computers are good at to expose the possibilities of this type of manufacturing to not just designers, but to anybody, so we can lower the barrier to creation. A lot of projects that we do start with a natural phenomena. Our hyphae project from 2011 was inspired by how veins form in leaves. We ultimately translated that into an algorithmic mathematical system that we could use to explore how these forms emerge, both sort of exploring the natural pattern space of what is possible in nature, but then also starting to create different types of things that aren't represented in nature, thinking about it as a broader type of design tool. So leaves are flat, and the veins you see in them are flat structures, but what if we apply the same logic of that algorithm of growing towards sort of hormone sources to 3D? What do we get then? We get this, apparently, this uninterpretable, bushy, branchy thing. But what if we start to impose some sort of order on that? We can control parameters of how it grows. We can ask it to be sort of more dichotomously branching in one area and then affect it in ways to create a more dense reticulated structure. Ultimately, we translate all the things that we design, all of our research and weird ideas into everyday products. So our hyphae system, all of that ended up going into our lamp collection from 2011. Every lamp is one of a kind. The customer can select, exactly which one they want, and it sort of one of the things we do is marry the infinite possibilities of algorithmic systems to the infinite materialization possibilities of 3D printing. Why use 3D printers to make something over and over again? Why not open that up to variation? And, you know, different shapes, cool lamps. Okay, so another project, this one I actually started when I was a student here. It was called Cell Cycle. And it was inspired by radiolarians because all architects love radiolarians, apparently. But in fact, it was really looking at, you know, can we play in this sort of space of cellular forms? You can make forms like these in, let's say, Maya or any other software, but with great difficulty, essentially. A lot of like very careful modeling, very careful scripting. But how can we sort of explore the incredible expressiveness of this? And then how also can we take advantage of this maybe to make 3D printed products that use very little material that are very efficient? So I think actually in 2009, we published our first 3D modeling tool for the internet. This runs completely in your browser, and it's sort of a web application for modeling complex cellular forms. Oh, actually, can we turn the sound off? I have all sorts of sounds that I don't want to hear. So, I mean, you can essentially see what it does. So the idea is, you know, how can we create really lightweight, real-time interactive design tools for the web that let you do the things that we want to do with 3D printing, make complex forms, make unique things that fit you directly, that are your style. And then how can we do fun things like, you know, since you're live modeling, let's live calculate the volume of your design and give you live price updates. Let's make it so you can save your design and share it, send it to other people, you can tweet it, they can start editing it, and you have this branching proliferation of designs. You can subdivide things and sculpt them, you know, all that good stuff that we like. So yes, we develop a lot of things like this, which are sort of, I guess, at the cutting edge of web technology, but turning it into essentially like tools for product design. And people have made a lot of things with it, mostly jewelry. We tend to work at the scale of jewelry because it's an affordable scale for both us to work at and for other people to purchase our products. So we're really interested in sort of the diffusion of all of these things into everyday life, and this has been a good vehicle for us. People have made a lot of things like their own wedding bands and other pieces that they give to people which are very meaningful to them. And that is interesting. Okay, so I'm going to talk about a project that we're currently working on called Floriform. And this project deals somewhat with differential growth and the development of form in biological processes. So there's numerous questions in that, but for instance, how do organisms go from a single cell to a complex differentiated structure like a human being? If a single cell were to divide and grow uniformly, it would essentially result in a formless blob. However, through carefully coordinated subdivision and differentiation, biological systems produce structures with specific reproducible forms and functions. Essentially, you have a structure where some areas grow more than others, and you end up with a shape, let's say. And there's all sorts of interesting questions underlying this. How do underlying cellular processes produce macroscopic shapes, and how do those macroscopic shapes then influence the underlying cellular growth processes? How do cellular growth processes interact with the mechanics of biological materials? And the mechanics of biological materials is the part that we're sort of dealing with more specifically in this project. Maybe a very naive look at differential growth, something that you see every day is a plant growing towards light, phototropism. How does that work? You essentially, if we dumb it down to a two-dimensional diagram, you have a differential elongation of cells to produce a three-dimensional curvature. If you think about that as a surface, maybe you have two layers of surface. One is growing faster than the other, and that produces a defined curvature that could explain, let's say, the blooming of flowers due to temperature differential. We were really interested in these types of ruffled forms that you see on the edges of leaves and flowers. In particular, that they have a very complex curvature that seems maybe at first glance to be difficult to describe. If you were trying to turn that into a 3D model, it'd be pretty hard. And if you were describing it in terms of surface-based growth, like grow a little bit on this side and then on the other side, it'd be really hard to produce this geometry. However, a professor at Harvard proposed a very simple explanation. His name is Mehrabian. He's at the Wyss Institute. And his explanation is, here you have a surface that's growing differentially from the edge. What if you just grow more at the edge? It actually, we think, can produce these types of structures. And in fact, the more I got interested in this, I started seeing them everywhere. The arms of jellyfish, lettuce sea slugs, bryozoans, leather corals, et cetera, all sorts of things display this growth model. So we built a mathematical model of it. I don't have time to go into all of this, but if you're interested in math, ask me about it later and I'll gladly go on at long detail. But essentially, we're dumbing everything down, all the complexity in a leaf or a petal, into a model of linearly elastic materials. So we have a mathematical model, and the first thing we do are explore different base scenarios. Let's say, what happens if you grow uniformly? This is a hemisphere, it's just growing the same everywhere, and we get this wrinkly blob that I predicted. This is maybe undifferentiated growth, nothing different is happening. Now, what if you grow from a point, and that point splits? This is very similar to what happens in plants when you have a single growing point, the apical meristem. What if instead of letting your point split, it lengthens, produces apparently this sort of shape? It's actually kind of similar to a mutation that happens in plants called fasciation. Here we get to the last one, growing more at the edge than everywhere else. Ta-da, it makes the cool convoluted shapes. So this is like at the very early part of a project. You have a basic model of some physical phenomena. This is a physics-based model of an elastic system that we can control and manipulate in some ways. But how do we go from there? How do we work with it? And this image for me sort of represents our philosophy of how we work with dynamic systems. So I describe our practice almost as a kind of digital gardening, but instead of cultivating plants, we're cultivating algorithms. And we ultimately want to create or breed systems that have their own innate behaviors, but that we can also sculpt and manipulate. So as we're developing the software, we're constantly encoding sets of influencers, gradients, manipulators, et cetera, that allow us to sculpt or interact with the system as it's growing. And there's an interplay between what the system innately does and our manipulations, and this back and forth sort of continues to change as we go and recode and reconstruct the simulation. So just to give you an extremely brief idea of what I mean by that, imagine you have 3 identical surfaces that are growing, and they have different bend strength. They resist bending a different amount. What happens then? Well, apparently it changes the wavelength of the surface. Or something even simpler, imagine that they're infected by environmental gradients. So the one on the right, in the sort of bottom right area, has more potential to grow in that space, let's say due to nutrients or lighting conditions, whereas the one on the left has a more uniform distribution. How does that affect the growth? And we can ultimately, change those through space, through time, to produce very specific types of effects that we're interested in. Okay. So this is a surface that's changing thickness through time, and I'm also letting you see what's going on. So we're doing a very complex mathematical simulation on a triangular mesh with collision detection and other things, and that constantly has to be essentially subdivided, edges get flipped to keep the triangles nicely shaped, which is how you do math on a surface. At this point, we're very early in the project. We've translated some of the things that we've been exploring into 3D printed sculptures. The one on the bottom is one of my favorites because we've essentially sort of hooked up 2 algorithmic systems together. The one that I was talking about that does leaf veins, and this one that sort of does leaves, if we're dumbing it down a lot, to see what happens at the intersection of those 2 things. We're also experimenting with using full color 3D printing to make sculptures that express the growth rates that determined the form through color, so that gradient of color expresses the geodesic distance between growth zones. And also playing around with 19th century zoetropes to produce objects that grow before your eyes and express the algorithm when you just look at them. And then we're also working on a jewelry collection. As I hinted at, nervous system sort of thing is that we think that really complex ideas about the world around us, about science, about technology, shouldn't just be limited to academia and research. Why not have them diffuse into everyday affordable objects? That seems like a good idea. And I don't really have anything to say about this, but this is an example of one of the growth processes we use to create one of the pieces in the collection. So you can see sort of the degree to which we can control the system, produce very specific types of results. Okay, I have no idea how I'm doing on time, but I'm on my last project, so probably we're good. Okay, so this is the project that I've been working on last year called Kinematics. And this project reflects more of our focus on digital fabrication and co-creation. It isn't really inspired or based on nature in any way. So 3D printing opens up a lot of new possibilities for creating different types of materials. I'm interested in textiles in specific because they're sort of man-made materials. They have certain raw fiber, and then based on the arrangement of that fiber through space, we're creating different types of behaviors. And they're also sort of historically computationally mediated. You have things like the Jacquard loom, invented in 1800s, have always sort of had computation embedded in the process of producing textiles. 3D printing lets us make all sorts of new material configurations through space, so maybe we can use that to create more sorts of constructed materials like textiles. A project that I worked on for Google in 2013 led to me creating some sort of bracelet-like wearable objects that have a kind of hybrid behavior between hard and soft. And we were interested in exploring these things like past the scale of jewelry. So we'd made bracelets, and those are well within the size of a 3D printer. But what if we could expand past the confines of a 3D printer to make something bigger? Like, how would this hard, soft material work if it was a long, flowing dress? How would that move and behave? So we started thinking about, well, how would we make a bigger thing? Lots of digitally fabricated projects that do this sort of follow the same idea. I have a big thing I designed in a computer. I want to make it. I'm going to chop it up into thousands of tiny parts, print them all separately, and then through great expense, I'm going to organize them by hand and assemble them. And often that sort of assembly task takes far more time than the design task did, which seems kind of backwards. You've used computation to make your problem much, much bigger. So we were curious, maybe we could print something bigger, but as one thing, and maybe we could do that by taking advantage of the fact that our structures are flexible. So what if we have these flexible structures, we scrunch them up before we print them scrunched up, and then we unfold them into their final configuration. So that was sort of the seed of this project. And once we started thinking about, you can make big flexible structures all in one piece, we started thinking about clothing in general, and then we were thinking, well, if you can make clothing in 3D, that changes the whole idea of how people make clothes. Normally people have a 2D pattern that is mapped onto a 2D piece of fabric that's cut out, and then it's sewed together painstakingly to reassemble a 3-dimensional shape. But if we can make something with a 3-dimensional shape at the beginning, then we can do the entire process in 3D. We can capture your exact body shape with 3D scanners, we can let you design it, and then we can just print it. So we thought that this was worth working on. So we started working on it, but there are lots of avenues of research to do. Problems to do with 3D printing, material strength, tolerances, error, print orientation, machine size. Problems to do with designing. How do you design these structures? How do you make it so anybody can design these structures? They're very complex. You'd be hard-pressed to 3D model any of these by hand in any traditional CAD package. And then how do we capture your body data? How we can make sure that your garment that we make from that data will fit the body? And how do we actually do the simulation that I claimed we could do, which is really the heart of the entire project? And I don't have time to discuss any of those in depth, so I won't. But we did make this web application similar to the cell cycle one I showed you, except for it's designed so anybody can create their own garments. There are sort of different aspects to it. You can create your exact body shape. Then you can go in and sculpt the form of the garment. You can sort of construct the textile itself, so the pattern of small and large triangles that define the sort of performance and behavior. You can save designs. You can share them with your friends. You can all edit them, the whole thing. At the heart of it is this remeshing algorithm that's happening constantly. So as you paint different densities of triangles, we're constantly recalculating the mesh in real time to show you the results of your interaction. And then you can go in and specify these different module styles. So right now this project is sort of like we did the most obvious thing, like let's make the easiest 3D modeling program for clothing. What do you want to do? You want to change the shape, you want to change the pattern, and then let's have some different style patterns you can put on so you can make a solid dress or perforated dress or tetrahedral protrusion dress or really anything in between. You can map any garment from any body to any other body. So we're partnered with a company called Body Labs, which has a machine learning parametric body model that they've constructed from thousands and thousands of scans. They sort of have fixed our data problem of how to map from one body to another because they have this model that we can work off of. And then we get to the heart of the matter, which is the simulation. So originally we had a naive idea, let's just crumple it up and shove it in a box. And if it fits in the printer, that's good enough. It doesn't need to be efficient, it just needs to print. But when we got to the point where we were actually ready to make a dress, we were like, that's not really good enough. We actually want to use simulation to optimize, not just to make it possible. So instead of thinking about crumpling it up, we actually just thought about something even more naive than what we originally thought of, which is, oh, we should fold it. Like you're putting a shirt in your dresser, why don't we fold it? So we created a rigid body physics simulation that we can use to interactively fold garments to reduce their size. So this dress we reduced in size by 85%, making a very condensed volume that it can be printed in. And in addition to that, it's not just about optimization, but it's about understanding the behavior. So if I'm creating a dress made out of 5,000 interlocking unique components, I should probably see how is that going to drape and move? Like, how does what I'm designing actually affect what it does? So we created a tool that allows us to understand how the dress will drape and move, and then we can use that to feed back into how we're designing it. So we actually made the dress. That's a somewhat recent development. It was printed all in one piece, as I've been telling you, which is exciting, and then they dig it out of this powder, and the video is somewhat boring, but yes, we'll just move on. So ultimately, we ended up with this garment. One of the main things that I was interested in is making it actually wearable, because there have been a lot of 3D printed garments making that are advertising how amazing 3D printing is, but they're fragile and uncomfortable, and they're more like sculptures that you would wear. So I was thinking, this doesn't express the potential of technology to me at all. I want something that anybody can design, that anybody can wear, that will fit any body type. So that's what we set about to do, and I feel like we're getting there. I've worn it, I've sat in it, I've danced in it. It's pretty cool. One thing we were really interested to see is how well would the draping of the garment in real life reflect our simulation that we did to predict how it would behave. And they're quite similar, so that seems good, useful. And here we have the final-ish slide where you can see the finished dress. Let's see. So this custom fit dress is an intricately patterned structure of more than 2,200 unique triangular panels connected by more than 3,300 hinges. They were all 3D printed as a single piece in nylon. While each component is rigid, in aggregate they behave as a continuous fabric, allowing the dress to flexibly conform and flow in response to body movement. Unlike traditional fabric, this textile is not uniform. It varies in rigidity, drape, flex, porosity, and pattern through space. The entire piece is customizable from fit and style to flexibility and pattern. For us, this is kind of just a very first baby step towards a larger project about how can we leverage digital fabrication and simulation to create complex digital materials and products. And I guess how can we empower the design process through using these types of simulations? And I do believe that I have concluded my presentation.
Like we did this morning, we're going to take the questions at the end of all 3 talks. So I'm going to just briefly introduce our next talk. Alma Steingart is a junior fellow in the Harvard Society of Fellows, which is sort of an elite society, no pressure there. So Alma has been like examining mathematical abstraction in mid-century America, and recently more placing the emergence of new mathematical epistemology in the cultural and political milieu of the Cold War. And she's also interested in, she is also investigating the introduction of computer graphics in mathematical practice in the 70s. I think she's always mainly been interested in how mathematics and physics have been intersected in multiple ways. And in general, like the new techniques by which mathematicians represent abstract ideas in multiple media, such as 3D physical modeling, early computer graphics, and immersive virtual environments. So she's really telling us all the sort of, I feel like it's almost all the sort of backstage of most of our research elements. Yes, so without further ado, Alma, thank you for joining us.
Can we get the volume back up? Because I'll have a few animations that have on the volume. Thank you. In 2010, topologist William Thurston collaborated with the creative director of Japanese fashion house Issey Miyake, Dai Fujiwara, on their fall collection entitled 8 Geometry Link Models as a Metaphor of the Universe. The collection was presented at the Paris Fashion Show and was influenced by the time Fujiwara and his team spent at Cornell University attending Thurston's seminar on topology and geometric group theory. From the New York Times style section to Wired magazine to the notices of the American Mathematical Society, the show garnered attention from an eclectic array of media outlets. Needless to say, Thurston was a newcomer to the Paris show world. But among mathematicians, he already had a celebrity status. In 1983, Thurston received the Fields Medal, which is the most prestigious prize in mathematics, for his work on low-dimensional topology. His fame was mostly due to his geometrization conjecture, according to which a certain class of 3-dimensional manifold can be canonically decomposed into parts, each of which admits only one of 8 possible geometric structures. Now, the exact meaning of the theorem is really not important, but it does explain the name of Miyake's collection. Now, such collaboration might appear strange at first, but considering Thurston's approach to mathematics, the bond between the two men become clearer. Despite working in an area of three-dimensional topology, which by definition defies our perceptual capabilities, and I'm going to say a little bit about this soon, Thurston has promoted throughout his career a tangible, hands-on, intuitive approach to mathematical research. He used to build models out of paper, and he collaborated with other mathematicians on illustrating his ideas. In courses on geometry and topology, Thurston used cardboard and glue, as well as fruit and vegetable peelers in order to teach students about complex geometrical concepts. So in fact, it was Thurston's realization that both he and Fujiwara required their students to peel oranges in order to investigate how three-dimensional forms are constructed from two-dimensional surfaces that led to their collaboration. In the 1980s, it was this tendency towards hands-on, materially mediated approach that propelled Thurston, together with several colleagues, to promote the use of computer graphics in mathematics as a way of creating a lively engagement with topological theories. Now, topology can loosely be defined as the study of qualities of space that do not change under continuous deformation. Unlike in geometry, topological surfaces do not depend on a metric. Rather, one can stretch and twist a surface without really altering it. This is why topology is sometimes referred to as rubber sheet geometry. From a topological perspective, for example, a sphere, a cube, and a cylinder are one of the same thing because one can smoothly deform one into the other. And just as an example, this is not true about the torus, or what's known as what's actually is a donut, which is not the same as a sphere. And the basic idea is that the torus, the donut, has a hole in it, which is why it cannot be deformed into a sphere smoothly. Now, the title of this panel, Programming the Physical World, therefore, seems to conflict directly with the work of the mathematician I here describe. In appealing to computer graphic, topologists' goal, after all, was to break free from the physical world. It was the abstract mathematical world that they wished to program. Note, not the physical one. Yet, what I want to suggest is that by approaching their investigation from a phenomenological perspective, paying close attention to the strategies they employed, the research speaks as much about the world we inhabit as the one that we can only dream. Moreover, in constructing models of non-Euclidean and higher dimensional geometry, in seeking to extend viewers' perceptual capabilities and challenge their apprehension, and in working with and developing technological media, these mathematicians effectively configured the world around them. And just to know, this is not limited to a mathematician. Behind me, for example, is an artistic rendition. Homeomorphism is the name of the map by which topologies transform one space into the other. Mathematicians were early to recognize the potential use of computer graphics in scientific research. And in doing so, they followed upon a longer mathematical tradition that incorporated illustration and three-dimensional models in both research and pedagogy. At the end of the 19th century, for example, three-dimensional plaster and string models were common fixtures in mathematical centers around the world. And actually, a little bit later, they kind of became interest for several artists as well. Yet, starting in the 1920s and in the 1930s, this intuitive approach to mathematics fell out of fashion. It was eclipsed instead by a formal and abstract approach. So it was only with the introduction of computer graphics that mathematicians turned once again to visualization. Already in the 1960s, the late 1960s, when computer graphics was really still in its infancy, consisting only on vector graphic display, Brown University mathematician Thomas Benchoff, on the top, collaborated with a computer graphics specialist, Charles Strauss, began exploring how can the new technology be used to visualize four-dimensional objects, such as, for example, the hypercube. What Benchoff did was to compute the shape of the shadow of a four-dimensional object in three-dimensional space. So in the same way, let's see. Yeah. In the same way that we can watch a shadow of a rotating three-dimensional object changes on screen, the computer display can serve as a three-dimensional screen for this four-dimensional rotating cube. So that's like what would be on the bottom. And I just want to give you a little idea of, if you haven't seen some of these films before, how these films look like. What was the? So this was made, I think, in like 71 or 72. This is not a hypercube; it's a different four-dimensional surface. As computer graphic technology developed in the following 2 decades, other mathematicians joined bench-off and began asking what can be gained by approaching mathematics using computer graphics. Yet, it was only in the 1990s that these discrete efforts coalesced around a central organization. The Geometry Center, an NSF-funded science and technology center at the University of Minnesota, was funded following a proposal by 13 notable mathematicians and computer graphics specialists as the first center dedicated to the investigation of computer graphics in pure mathematics. Thurston was among its leading members, and his research served as the inspiration to the first 2 mathematical animation produced at the center. So today, I'm really going to talk only about 2 of the films produced in the center, entitled Not Not and The Shape of Space. Outside In shares very similar characteristic to the other 2. All 3 films were pitched in an elementary level. Their producer hoped they will be accessible to the lay public, and so they included a fair bit of introduction to the subject. Yet, despite this, it's really worth noting that Not Not and Outside In reported on what at the time was actually quite advanced area of research. The results that they describe were relatively new and would have held interest to any mathematician interested in more intuitive understanding of the subject. In appealing to computer graphics, the member of the Geometry Center hoped to use data-driven computation to transform abstract mathematical theories into virtual phenomena. In doing so, they embarked upon a highly embodied imaginative work, integrating their visual, haptic, tactile, and kinesthetic perception. So, Not Not, the first film, introduced viewers to hyperbolic geometry and knot theory. Hyperbolic geometry is distinguished from Euclidean geometry in that it breaks with the parallel postulate. And I will say that actually in Jessica's presentation, the sort of leafy, that's kind of an example of actually hyperbolic geometry. So given a line and a point in hyperbolic geometry, there are at least 2 distinct lines through the points that do not intersect the original line. So where in Euclidean geometry is said to have 0 curvature, hyperbolic geometry has a negative curvature. And maybe another way to describe it more common, that where in Euclidean geometry, if we take the sum of the interior angles of a triangle, we get 180. In hyperbolic geometry, it will always be less than 180. And a mathematician have used 3-dimensional models and illustration to study non-Euclidean and higher dimensional geometry for decades. However, these models were always external to them. They were able to observe or touch the model of a non-Euclidean geometrical space, but they remain outside of it. What the producer of Not Not set out to do is to provide viewers with an experiential introduction to hyperbolic geometry. The film entices viewers to imagine what it would feel like and be like to live in such a world. What sort of qualitative perceptual changes would you experience? Stated somewhat differently, how would one know if one was living inside a 3-dimensional hyperbolic manifold? Now, manifolds are topologists' favorite object of study. They are spaces that locally resemble Euclidean space, although globally they can have a completely different geometry. So Earth can serve as a really good, useful guide here. In our daily life, we perceive of the surface of the Earth as flat, although we know that it's actually a sphere, right? So if we look at Earth from the moon, we see that it's a sphere. But how can we determine the shape of a 3-dimensional manifold we inhabit? The only way to see it from the outside would be to look at it from a 4th-dimensional space. And since this is not an option, the film asks the viewers, how can we recognize a hyperbolic manifold from the inside? So behind me you can see this is the moment in the film when the sort of viewpoint of the viewer switches from an outsider to an insider perspective. And the narrator can exclaim, "We're escorting you into Lobachevskian or hyperbolic geometry." Now, I want you to listen to, in the next clip that I'm going to play, what the narrator is asking you to do.
Let's fly around a little in hyperbolic space to get a better feel for it. Notice how quickly apparent size changes as we move. This is one of the biggest qualitative differences between our everyday space and hyperbolic space. This is what it looks like to live inside the space created by order 4 axes along the edges of the dodecahedron.
So it might be hard on first watching this to pay attention to all the various features of the space and how exactly differ from our everyday experience. And if you are feeling somewhat distorted, it's probably worth noting that the Grateful Dead used this video in their 1990s during their concerts. The film does not provide a model or define what hyperbolic space is, but rather it transforms it into a lived experience. In doing so, the film pushes back the horizon of what is mathematically perceptible and opens up the mathematical rim to visual exploration. Now, The Shape of Space was produced 6 years later. It was based on a book of the same name written by MacArthur Fellow and student of Thurston, Jeffrey Weeks. And like Not, the aim is to give viewers intuition into topological spaces that differ from our own, specifically spaces that are finite yet boundless. So an example of such a space is a 2 torus or just a torus. We know that the surface of the torus is finite, but we can't see a boundary. If there was an ant that's living on the surface, the ant will never arrive at an obvious kind of stopping point. So the animation spends some time explaining these ideas, but the goal is not really to understand the 2 torus, but to understand the higher dimensional analogy of the torus, what's called the 3 torus. The surface of the 2 torus is 2-dimensional, so we think about it as hollow, right? There's nothing inside, just the surface. The higher dimensional analogy is a tora in 4-dimensional space whose surface is 3-dimensional. And if you're somewhat confused, here's a demonstration of what it might feel like to live in such a space.
Let's ride the spaceship inside the 3 torus.
The music is wonderful.
Even though the 3 torus is finite, we have the illusion of flying in an infinite space. There are only 2 stars in this universe, but we see each one over and over.
So there are 2 noticeable differences here that are evident in this later film. First, the viewer is now placed inside a spaceship, and it's through the active navigation that one is supposed to get familiarized with the space. Second, the space is now populated with objects. As the narrator explained, while there are only 2 stars in this universe, you will see infinite copies. Now, the reason in principle is that the rays of light would not behave as we expect them to. They will wrap around the space, reaching you from various directions. And if you're really curious, I should say all of those films are available on YouTube. And in fact, on Jeffrey Weeks' website, the last time I checked, also we had games that would teach you how to have an intuitive understanding of living in a 3-dimensional torus. For example, you can play tic-tac-toe in that, and you will always lose. I'll tell you that. But you should go and check it out. But the point I wish to draw attention to here is that by calling upon viewers' imaginative navigational skill and by populating the space with objects they can relate to, the film calls upon the viewer's perceptual capabilities even further than before. And this approach is motivated by Thurston, who noted that words are one thing. We can talk about geometric structures. There are many precise mathematical words that can be used, but they do not automatically convey a feeling for it. What does Thurston mean by having a feeling for a geometric structure? And how does it differ from our understanding of its precise mathematical formulation? According to Thurston, there is more than one way of knowing geometry. Formal abstract mathematics provide with only one mode with which to apprehend hyperbolic space. Imagination is another. And computer graphics could help train a topologist imagination. Of course, in aiming to provide viewers with such an experience, Thurston and his colleagues were restricted by the technological medium. The lighting in the animation, the first animation that I showed you, was computed according to a hyperbolic perspective, but the screen mediated all engagement. But it is exactly this feature of the work that make topologist exploration extend beyond the world of mathematics. In the act of trying to imaginatively apprehend non-Euclidean geometry, topologists were forced to query into the nature of human perception, asking questions such as, on which senses does space perception build? How can technological and material exploration augment one's perceptual capabilities? And what is the relation between understanding and sensually apprehending? Such a connection between topology and perception was drawn before, albeit in a reverse way. Not how can theories of perception inform topological research, but whether topology can serve as a model for theories of perception. In his notes that were later published posthumously in The Visible and the Invisible, Merleau-Ponty directly drew such a connection. He wrote, if Euclidean space is the model for perspectival being, topological space, on the contrary, is a milieu in which are circumscribed relation of proximity, of envelopment, etc. Topology, Merleau-Ponty proposed, offer a model for human perception that broke away from Cartesian epistemology. Instead of positing a knowing subject and an objective world exterior to that subject, topology reaffirmed the whole body as the site of perception. According to Merleau-Ponty, a fateful mode of embodied perception required a topological conception of space, a qualitative rather than a quantitative approach. I describe perception as a diacritical, relative, oppositional system. The primordial space is topological, that is, cut out in total voluminosity, which surrounds me, in which I am, which is behind me, as well as before me. Space did not extend in front, but expanded around the subject, seeing and being seen, touching and being touched. Now, such a statement, perhaps as poetically, could have been stated by Thurston. In trying to experience non-Euclidean geometries, topologists had to imaginatively extend their perceptual capabilities. What they affirm in the process is that space perception is not restricted to vision, but rather requires an embodied subject, attuned to tactile, kinesthetic, and motor cues. So I want to play for you a final clip. This one is not from a computer animation, but from a lecture that Thurston gave in 2010 at the Clay Mathematics Institute. So in front of a big room full of mathematicians, Thurston explained the properties of a specific manifold.
That doubles the world. So we have a loop here, and when you pass through the world, suddenly you're in the United States, and the coffee is brown-colored water. You go through the loop again, and we're back in Paris, and the coffee means something.
So the topological space Thurston described is not an object of knowledge which is exterior to him, but rather one he inhabits. His apprehension is fully embodied. Topologists' film built upon optic technology, but they demanded the viewer to imagine themselves as moving around such constructed spaces. They incite them to transform formal mathematical expression into imagined kinesthetic experience, and to accomplish that, all they require are the techniques of the body. Exploration of topological spaces, whether material or digital, were by their nature also inquiries into human perception, its extension, mediation, and limit. So to conclude, maybe such exploration reveals that imaginative work is itself a form of design. Thank you.
Well, thank you so much. And the coffee is not so great in Paris anymore. I don't know if it's just a myth, but I can confirm. It's much better in Italy. Anyway, so our last talk is Gentiane Venture. Sorry, it's the English, French. So she's a roboticist now working in Tokyo. She heads her own research lab, GV lab, at the Tokyo University of Agriculture and Technology. I should be able to remember that. And she's an associate professor there. She's trained basically as an engineer, and she's been she also obtained a PhD on modeling and identification of car dynamics from the University of Nantes in France. And so she's researching mostly human-robot interaction in public and private spaces and investigating how robots interact with us. And her talk is really going to show us how we can use human motion data to create robots that are going to be more and more familiar to us and with us. So thank you.
So thank you, Joël, for the introductions. Thanks a lot for inviting me there. It was a long trip to come for Tokyo for this event, but it was really worth it. And I'm completely jet lagged, but I didn't fall asleep so far. So I'm just waiting so that we can switch to the HDMI input. OK, so we're good. And I'm going to show you something very more practical and down to earth, rather than the presentation that we've been hearing so far. And I'm going to start by showing you a small experiment that we did in our lab, and that has been the starting point of a lot of new work starting on how people perceive robots and how familiar do we need to be with robots and robots needs to be with us, and how we perceive all these interactions. So one day on a campus, we asked people that were walking around if they wanted to come to our lab and to participate in a small experience that was consisted in filling a questionnaire about robots. Nothing too complicated. A lot of people said, no, sorry. OK, good. Finally, after a lot of trials, we managed to gather a lot of people because, of course, few people said, yes, sure, they were interested in filling a questionnaire. What's very exciting about filling a questionnaire, I don't know yet, but anyway, they were OK for doing that. And then we just tell them, well, for the purpose of our experiment or analysis, we will record a few data while you are filling this questionnaire. OK. And basically, we will record your motion data. Well, basically, when you write, when you move, we will record how your head is moving and how your hands are moving. OK. So please sit down, make yourself comfortable. We will bring in the questionnaires. And that's what happened, basically. Basically, participants were seated. So we are in Japan, so they are seated on the floor, so that's normal. And while they were seated, they were waiting together. We asked them to come by pair. And instead of having somebody bringing the questionnaire, we had this silly small humanoid robot bringing it in. So the robot was bringing 2 envelopes with questionnaire inside, and people had no instructions. Our participants were asked to fill the questionnaire, but we didn't tell them how we will bring in the questionnaire and what they are supposed to do with these. So a lot of people understood that actually there was written questionnaire on the envelope. Well, actually, it was not written questionnaire. It was written in Japanese, but it was still written questionnaire in Japanese on the envelope. So most of them would take the envelope from the robot while it was delivering the envelope to them. A few people didn't even bother taking the envelope. They didn't understand what was the point of the experiment or the point of all this. And the robot was a bit playful. It was not behaving the same way it was with the participant on the right side and with the participant on the left side, so that we mixed up experiences. And in the envelope, there was actually a questionnaire about robots. And we were actually measuring their head and hand motions when they were interacting with the robots. So this little robot is called Nao. It's a French robot built by a company that's called Aldebaran. That is now is the Japanese company. And so basically, that's how it was going on. So what we see here is that the whole experience is nonverbal. The robot didn't say a word, and participants were allowed to talk together, but we didn't specify anything. So most of the time they were like looking at each other, smiling at each other, acknowledging with each other, but they didn't really talk together. And what we were interested in is to see how these like nonverbal interactions was correlated with the way they behave with their emotions. Why we're interested in that is because in the literature we can find that 93% of our communication and human communications is nonverbal. That's quite a lot, right? So basically, without even saying any words, we can communicate a lot of information. And this is not very recent work, so it seems to be quite valid even now. So this like nonverbal communication, well, basically, it's motion data. So it's motion of like whole body motions. It can be facial expressions. It can be a lot of things. In our case, we are only interested in what we call kinematics and dynamics in the robotics world, in the engineering world, which basically for everybody could be body language. The way I move my arm, the way I move my body, the way you can feel I can be like a little bit stressed speaking in front of you, or I'm completely like super happy, and these kind of things. So this information is actually super rich in information. This data is really rich in information because it gives us information about what we are doing, the action that we are performing right now, about who we are, because everybody has a different body language signature, and it gives you also information about your emotions, what we are feeling at the moment we are performing, interacting, discussing, and these kind of things, and about your health. Health, today we won't speak about it, but it's also something really important. So using this nonverbal communication, this body language, we were interested in trying to find what is a successful human-robot interactions or human-machine interactions in more general or in broader sense, if you want to see it that way. So how can we use the motion information to create a satisfying human-robot interaction in the case of this interaction or in any case in general? Because as you may imagine, in the future we will probably be surrounded by tons of robots if it's not already the case. There are some freaking scary robots. The one on the right side is a Japanese robot that has been actually used in classrooms for probably primary school or like super young kids. We have like the seal robot that is used in Japan also to heal like elderly people with dementia. A lot of people might know the Roomba robot, the vacuum cleaner robot, the lawn mowing robots, these kind of things. Baxter, that is also from Boston. That is a robot that is used in factories, but that interacts with human. And of course, you see two of these like robots from Aldebaran Robotics. Pepper, that was supposed to be sailed in Japan for a very cheap price, but which launching has been postponed again and again. And the small robot that we were using for our experiments, which is a very common robot used in robotics research. So all of these robots are supposed to interact with us somehow, someday, in the near future or even already now, but it's not so easy to build up a real human-robot interactions, right? I mean, even building a human-human interaction is not that easy. I mean, anytime you are interacting with somebody, and in particular at the very first time, when you have never met this person, it's always a mixture of emotions, of sensations. There is a lot of ambiguity in what we are perceiving, and with the robots, it's even worse, because there are a lot of things that we don't know, a lot of things that the robot doesn't know, and that is not programmed for, because so far robots are programmed to interact with us. So how these nonverbal interactions, this body language, can be used for human-robot interactions is one of the key questions right now in robotics research. And basically, how the whole body motion, so again, this body language, correlates with how familiar we perceive the robot, because familiarity, perceiving the robot as being familiar or the interaction as being familiar, is one of the key to solve one of the problem of human-robot interactions. Because if you think that this robot is familiar, if you feel familiar with the interactions, then it's going to be much more easy to interact with the robot. So back again to this experiment. Basically, so we measured the head motions, we measured the hand motions, we asked the participants to answer the questionnaire, in which we were asking them to rate the behavior of the robot, to rate their perception of the robot, and to tell us a little bit more about their own history of interaction with robots. So most of our participants have never interacted with robots before. It was their very first time they were seeing actually a real robot, and they had to interact with someone, with these. I say someone, I'm sorry. And what we found with this very specific robot, Nao, was that basically the behavior of the robot was pretty much understandable. Well, the robot comes in, it's like both Japanese way of like saying hello politely. He ends the envelope, he say goodbye. That was fairly okay for most of the participants to understand. But none of the participants could understand the personality of the robot. Well, the question is, does this robot have a personality actually? That's also a problem, but still, if you want to project a personality to this robot, it was very difficult for them to do that. So it was difficult for them to see the robot. I mean, they were seeing it as a social entity, but not as a full social entity as humans. Then a lot of participants understood the task, because actually it was not difficult, right? It was just taking this envelope, but they were neglecting social interactions. So the robot was bowing, the robot was saying hello, goodbye, these kind of things, but they were just like ignoring that. Okay, give me this envelope. Goodbye. Well, cool. And then it was the very first encounter for a lot of our participants, but they rated the interaction as being very familiar to them, which is quite awkward for me, because like having a robot delivering me an envelope is not something that could be very familiar to me, but still it was. So that was pure ratings from the questionnaires. Now we are interested in how these like human-robot interactions and emotions relates together. So what we found that was quite interesting is that the way people were grasping the envelope, so basically taking the envelope from the hands of the robot, was correlated with their feelings, because we asked them to rate their feelings during the questionnaire. And there was a high correlations when they were grasping the envelope, the way they performed the motion to grasp the envelope, and what they were feeling. And in particular, most of the participants that felt the robot that was familiar to them had the same type of motion to grasp the envelope. So there were some kind of like completely, I mean, not unpredictable, but quite surprising results, that people that felt the same way had a similar manner in interacting with the robot. The other thing that was quite also interesting is that people, when they found the robot sociable, they had more intense and faster and more important motions when they were greeting back the robot. So not everyone greeted back the robot, but the people that found that the robot was a social entity, they were greeting back quite a lot. People that didn't found anything were not even greeting back. And some people didn't even look at the robot. So there is really something quite interesting here, is that like, so we have all this like information collected on motions, on what the participants felt, and this correlation together, saying that the emotions, the familiarity, and the way they interacted with the robot is highly correlated with the way their body reacted to the robot. So basically how they physically interacted with this, within this interaction. And it was very interesting to use all this information, but we were very much limited by the robot that we were using. We are using a commercial robot that has a very specific image I spare you the sound of the movies, but the noise that the robot now is making is extremely high, and the gears and the motors are very noisy. So it's very hard to imagine that robot can be, at this stage, an entity, a real social entity, when you have something that is doing all the time during the interaction. So we really think that it is a really important thing for us to design robots in terms of appearance, but not only the appearance, because we are here not with just an object, but we are with a moving object. So we also need to design the motion of the robot, the way the robot is interacting with the humans or with the environment, to try to solve the problem of like really seeing the robot as a social entity, not just as a tool to convey or to bring in envelope and to serve people. So we're now working on a very new project that is called the Metamorph robot. So it's a robot that can change shapes and appearance that I cannot disclose right now to you, but which it's just like a very new starting project and a very exciting one, where we are taking into account how the design of the robot and how the motion generation of the robots will influence the way people are interacting with these robots. And in particular, we are using a lot of humanoid-based systems, but we also want to investigate if humanoids, or at least anthropomorphic robots, are the best option for people to understand what robots are trying to do and to interact with the robots. So basically, I'm going to conclude here my talk. And I would like to thank all the people in my group that work in this project and that are going to work in this project. I would like to thank you for your attention.
Yes, thank you. So, wow, first, right? What a great diversity of talks addressing. I want to actually bring back trying to find some sort of common thread. And for me, what struck my mind was this relationship with the term of perception. And when you were showing the slide with the Grateful Dead, it made me really think of the doors of perception, right? The Timothy Leary kind of experimentation. And I feel like we're sort of having this relationship with the physical world and the material world where we live in, while we're dealing with things that are fairly abstract in a way. So in terms of how would you, and it's an open question for the three of you, how do you understand in the end the way you grasp the data that you're using, or the geometry, or the sort of range of motions in the case of the robots with the actual world that we live in? And how do you think the material culture that we have can resolve this tension between this abstraction and this physicality?
I mean, I can take a go on it. So I think that part of what, it's working, right? Yeah. Part of what's kind of
you have to speak in them.
Okay, I need to speak into it. So I think part of what I found interesting, at least in the cases that I was talking about, is exactly this idea of questioning about questioning the limits of perception, and that ends up always having, at least the mathematician that I look at, their work end up question the perception, their everyday perception eventually. So they're trying to both kind of extend it and mediate it, but that means paying very close attention to the way you interact with every kind of material. So the early the mathematicians that looked at kind of question about how do you going to visualize in hypercube, the first thing they talk about is like, if we look about it's things that if we look about a space and we look at a certain object, we understand the object, right? It's like about walking around, touching it. So it's this sort of understanding that then they wanted to bring into their computer visualization. This, like, again, they wanted to bring in this embodied way of thinking about space perception. But I don't think there's a way to necessarily, it's always trafficking between this sort of a kind of abstract understanding and this very material mediated engagement.
Okay, so in the case of the robot, if I may speak, the robot is basically, let's say, stupid and doesn't have any perception by itself. So everything that we can do is try to project our own perception on the robot itself and try to mimic or try to understand what could be human perception and try to put it inside the robot. On the other way around, from the user point of view, the perception is quite interesting because it's a very complex process. As some of the talk this morning were also mentioning, there is an emotional balance in the way people perceive the robots and a projection of what they are expecting from the robot, which basically in most of the cases leads to a great disappointment. Because we must say that most of our robots nowadays are just like unable to fulfill any of our expectations. Unless you have the vacuum cleaner and you're very satisfied with the way it's vacuum cleaning, other more complex robots are just like damned, and you can project as much as you want on them, but it's like projecting anything on your maybe goldfish. And even probably my goldfish are more intelligent than my robots, so.
I feel that there's always disappointment. The term disappointment is very interesting in technology, and nowadays, especially with the new emerging technology, there's a sense of deception or disappointment, which is interesting. Deception is actually the word of disappointment in French, but it means some sort of betrayal, which I think there's like, I don't know, Jessica, if you've have this experience in your line of work, because what I really liked about your talk as well is that in that sense of you wanted to ground somehow the investigation in digital fabrication and make it affordable and wearable. So do you have any conflict with the fact of the relationship between the expectation and the results or the outcomes? Or are you fairly satisfied?
Let's see. I guess, in general, since we make things that are intended to be sold to people and intended to be sold in some volume, like I'm not just making 5 limited edition things sold for $20,000, I'm making, thousands and thousands of things that I sell between $5 and $100. I focus very strongly on making things that won't disappoint people and focus on making them, durable and wearable and comfortable and all those things. So not only do I not have business problems, like everybody wants to return stuff, but also I'm sort of almost like an ambassador for all of these ideas and technologies to like everyday people who may not have encountered them before, and I sort of aim to make those first experiences not a terrible experience.
In terms
I don't know if I'm interpreting this question too literally.
In terms of the design process, I imagine before you actually sell the produce, maybe is there like in your first tests or the first sort of expectation you might have on the behavior of material or the fabrication process itself? Do you find that sometimes do you play around with the limits, or do you sort of manage to get around them?
I'm still not sure if I'm totally understanding the question, but I mean, of course, everything like goes wrong, and your first idea of how you should build a system, it never works. And most of the projects that I showed, I've worked on for several years to get to the point where I am now. So I'm working on like 5 or 6 generative systems that may not get to the point where they actually do anything of value for a long period of time, because these things are fairly difficult. And yeah, there are all sorts of limitations to all the materials and technologies that we have today, but I guess part of what I like to do is figure out what can you actually do with them that is good, with the level of technology we have now.
Okay.
Seeing as I don't develop 3D printers and I'm not a material scientist.
Okay. Do you have a reaction, comments, questions to the talks that we've heard in this session? Yes.
Yeah, thank you all. Lovely talks. I just wanted to ask Jessica if you guys have done any analytics on the interaction with that interface. Like, do people build 100 dresses and then decide not to buy one, or like just how? Because it's a really interesting interactive tool, and I think all of the work is really great. I'm just curious if you've done any analysis on how the interaction with it is unfolding, both in terms of its being passed around and the individual user.
The short answer is no. I haven't done any actual analytics of that. I guess when it comes down to it, since our company just has like 2 designers / programmers / engineers / artists, we spend essentially all of our time creating this stuff, and we're not that interested in the analytics of it. Although I guess if I had a business manager or something like that, they'd be really interested in that. But I sort of have a sense of that, though. I mean, in general, we see thousands and thousands and thousands of designs ordered to of thousands of designs created to every, let's say, 10 or 20 designs ordered. So I think a lot of people actually come to the site with no intention to purchase anything at all. They just saw it tweeted somewhere, they saw it in a news story, and they are like, oh, I can play with this. I can get an experience of 3D modeling or creating my own clothing design. And then some small percentage of people actually might want to purchase something. Yes, we're constantly rewriting all of our code and apps. Since we started, there was no WebGL in 2007 when we started, so we've, since the invention of that, suddenly everything that we do got a lot better. We used to work with Java applets that were embedded on our site, and then we upgraded essentially to full JavaScript code that creates interactive experiences with no plugins and all of that stuff. And that spec is constantly improving, so we're just always, yes, rewriting.
Yeah, you need the microphone for our video viewers. Thank you.
So my question is for Jessica, but maybe something that others can speak to as well is, how are you approaching or thinking about external factors? So like you have the one organism that grows. Are you thinking about what if the light source changes, or there's the unexpected interaction between 2 organisms, and how you would model that?
So in general, yes. The project that we're working on right now, whatever it's going to be called, Floriform maybe, that one we're working a lot with things like gradients of environmental factors, so thinking about these things like nastic movements and tropisms in plants, which are responses to either directional, non-directional stimuli. So that's sort of a big inspiration behind this project. So we're of course kind of dealing with that, but we don't deal with everything in every project. Different projects have the aspect that is what I most want to explore. I haven't really done anything with things, different organisms that we're growing interacting. I guess in our leaf venation system, the hyphae system, there's this thing where if you have multiple things growing in the same hormone source, they might eventually merge and join, but that we don't do anything in particular at that point of interaction. So sort of no.
Yeah, thanks. Great talks. I have a question for Alma. Your computer animations that you've shown all seem to have the purpose of making these abstract mathematical spaces more sensory, making it accessible to sensory experience. So I was wondering, do you also have examples where these visualizations helped mathematicians in theory development? Yeah.
No, I mean it's a great question. I think so. Right. So the first part of this kind of project is they call into question what does it mean to understand a space, and then it kind of plays with the notion of what does it mean to understand a space abstractly as opposed to understanding centrally. But to answer your question, yes, this traffics both direction, because there have been so actually with the earliest film, the Thomas Bencher's films, he would create this animation, this very short animation, and those took hours of labor, because they were just like, there was a camera and they had to, it's like frame by frame, and then he was able to see things he was able to see things in the film that he didn't know before, and then he went back and proved it rigorously mathematically. But it was a way both of, I mean, you know, the film was not a proof because mathematician would not take any that would not be an evidence for mathematician, but it was an inspiration in a way of a new tool for exploration. And yes, there has been.
Hi, thanks a lot for your contribution tonight. I have a question for Yantian. You showed us all this research where you were trying to answer or propose, like, what is the relation of human beings with robots and how perceived sociability in those robots affects the way we interact with them and stuff. But I'm not sure if you conveyed in a way your desire for how that interaction you would want it to be. Like, I'm not sure if you talked a lot about analysis, but I'm not sure if I was wondering if you could give us like because you seem to like draw a line like, I acknowledge that there's this barrier that we probably won't ever surpass, but I'm not sure if you would want that to happen or not, or what is your feeling about this?
So the way the experiment I presented today was constructed was that we were given total freedom to the participants in interacting with the robot. So you can see it a way as like you build an object or something, and as this morning it was also mentioned, users can do whatever they want with it. So you can create a cup and they use it as, I don't know, whatever else. So basically the interaction with the robot was built in that way. So we didn't have any expectations about how people will interact with the robots, and we didn't want to have any expectations. Of course, we had secret expectations that the people that would like interact with the robot would understand that there was an interaction that was going on and they were supposed to do something with the robot, but we never specified anything. And we never specified anything because we wanted people to have total freedom in this first encounter, for most of them, with a robot, with a living robot, and interacting with this robot with a task-specific topic. The thing that was really interesting is that the questionnaire was designed by a psychologist to try to see how people perceive the robot and interacting with the robot, but without a priori that they would have interacted with it. So just like looking at it without exactly really interacting with it, they could also answer the questionnaire. And also, in the term we evaluate the questionnaire, we had no expectations because we were completely in the blue. We didn't know how people would react to this specific robot, this specific interaction, and everything. So basically, we just like put it in the room with the robot and let them do whatever they wanted. And that was what's really that is what is really interesting with robots, because in a lot of human-robot interactions experiments, the experiments are designed in the way that you conduct the participants to interact in a specific way, in a way that you expect them to react within the experiments. And this is kind of like biasing the whole experiments, right? It's like, okay, you give me a bottle of water, you expect me to drink, not to throw it at you. And the people could have like kicked the robot, touched the robot, and do these kind of things. Well, most of them didn't, but still, yes, it was like totally free in this interaction.
Rest assured that I understand your neutral approach to the scientific method of doing this analysis. I think I'm more in the lines of like asking personally what you would want the future of our relation with robots be. Do you see it more as like, would you rather have us be more friendly to robots, to like, or do you think you acknowledge that there's always be a barrier, and you like that barrier to be there?
No,
it's more of a personal question.
I don't expect anyone to. I mean, it's just like in human interactions, right? Like, you might expect that somebody's going to be nice with you, and then it's not the case. Or you might expect that everybody's going to like you, but it's not the case. And it's going to be exactly the same with robots. What is interesting for us is that it's like when you're interacting with like people, like in a public space. You want to have like a standard behavior for these people that comply with social rules and with like global rules in general. And then when you are in the private space, you might want to have this robot to interact differently with you, right? And what we are interested in is trying to create this like public space-based behavior for our robots and our more personal space behavior, and all based in these nonverbal interactions without like having to specify like please do that, do that, and these kind of things. And so as a roboticist, I'm very like skeptical about my own field actually. There's been a lot of research, there's been a lot of progress, but we are far away from like science fiction movies and these kind of things. So far, I love to have people interacting with robots as they might interact with other objects, like loving them like you may love your iPad or your computer or whatever thing. But I'm not so sure it's going to happen very quickly. Because of this aspect of like motion that is inherent to robot, we want the robot to move. And that is a very big problem.
Other questions? Yes, up there, up there. So we'll go from there and then come back.
Hello, I have a question for Alma. I'm curious, you mentioned of the Göttingen mathematical model collection and said that there was some sort of return to this intuitive models in mathematical education through the films. And so I'm wondering if you see a return the 19th century ways of understanding it, is that the aim? Do you think that's coming next, a kind of re-emergence of that?
So, I'm a historian, so I don't like to predict. It's not my job. But I think that it's definitely true that with computer graphics, there was a sort of a return to this sort of engagement and understanding. But part of it is not, so I think, so that's one way of telling the story. The technology came, computer graphic came, and then people, just kind of picked it up and technology. But I think that's just it's one level, but it's not the whole story. Part of it was really a reaction. So like I said, this kind of idea of how to, this approach that was very common in the end of the 19th century and actually really early on in the 20th century was really eclipsed by this abstract mathematics. So the best, and you see that in education, so the new math to people that like in the United States, the new math education, so it went all the way to elementary education, this abstract approach to teaching mathematics. So part of it is really a reaction to that. It's that that really just a reaction against people trying to go back and saying, wait, this is just one way that you can understand and you can study mathematics. There are more than one way. And that part of it was, so geometry, the sort of kind of higher dimensional geometry, obviously doesn't lend itself as easily to this sort of visualized approach. So part of it, the work of Thurston, that's why Thurston's work is important, because he kind of studied in two-dimensional topology and three-dimensional topology, which are kind of just at the level of what can you still perceive or can use still perception. So this is why he was very important to that. So there are a lot of levels. I think that computer graphic, it's true, mathematicians today use computer graphic a lot. And to say that this didn't have an effect on, or doesn't have an effect right now on research would just be not true the way students are being taught at any level.
There was another question, right? There's two more questions, okay.
I'd like to have a question for Alma. I think your focus from reality of topological space to hyperreality of Euclidean space. This is, I think, quite about. We need a certain degree of sensitivity about selecting our variables in space in any scale, not like just architectural space. Maybe it may be urban space. So how do you think once we decide to, let's assume that we have really very well designed tools, but how do you recommend to do that choosing the variables? Well, I just.
I mean, I guess that I probably shouldn't be the person that you're asking that question. You should ask somebody like designers. But it's. I mean, you probably just better than I. I mean, actually, I would be interested to hear your answer. But I would guess that it's a lot of trial and error part of it. But you would be interested.
Get to speak in the mic.
Sorry. I was trying to get you to answer the question.
I'd like to hear from Jessica as well.
Just because I feel like I mean, I can talk about how it's been done in research, but I don't know, and the goals are different than goals. I would assume that the goals for designers. So just because of that, I think that maybe Jessica will be able.
Yeah, please, if you like.
I actually somewhat zoned out because I thought the question was going to be for Alma. Was the question something about how do we choose what sort of variables we're exploring?
Yeah, I mean, well, space is a lot of scales, a lot of objects, a lot of things. So once we try to understand the art of some relationships, I believe we need to go deep in terms of some special, let's say, data, which is similar in its nature. For example, buildings different from trees. Trees are different from people on the street. So how do you recommend, if there essentially such categorization of the variables is essential, how would you think about it?
I don't know if I'm the best person to answer this question either, but I guess I fall into that like category of digital designer who doesn't specifically work with scale that much. In some ways I work with scale a lot because I'm materializing specific objects for specific uses that have extremely tight material tolerances, so I have to deal with it on that level. But another level I think about things more almost in terms of their dynamics and behavior than in terms of what size they're at. So I might see similarities between how city street grids act as network structures that have redundancies in them and how that could be similar to vein patterns that you see in leaves, those sorts of things, and how could you have, let's say, a set of partial differential equations that could describe those systems with similar dynamics, even though they have completely different way in which they arise. So in some ways, I completely don't think about scale. I'm like, oh, this giant leather coral is the same as this extremely small nanoflower that forms due to some process. So I don't really have any advice for you whatsoever other than just do whatever makes sense for you.
Hi, thank you all for all your talks were awesome. And I wanted to ask a question that probably it's between Gentian and Jessica, but I think the question could be answered by any of you or just one of you. So it seems like when we look at, both of you are really operating at the forefront of design, of technology in different ways. And Gentian, you were saying that you face a kind of constant disappointment with the interaction with robots. And I would say, Jessica, having seen the dress in person and here, I think it's a constant sense of delight to see this kind of work literally unfold before us. So it seems like, we have the technology, but our reaction to it can be dramatically different depending on, it could be a matter of scale, it could be, but not just spatial scale, it might be a kind of conceptual scale issue. And so I'm wondering, for this audience that is often involved in design and computation and social interactions, where do you see some of the key questions, like the forefront of research or exploration that might really break some of these constraints, either that produce a constant sense of disappointment or really push, Jessica, in your case, the technologies beyond even what you've already been able to accomplish?
I wish I had the answer, because if I had, I could go straight there and try to be not so much disappointed. But anyway, I think in robotics, and it's maybe the same in other fields where the science fiction has been abundantly writing and shooting about, our expectations are extremely high. We're all expecting robots that are like iRobots or even like D2R2 or these kind of things, right? But we're far away from that. That's just the point. We do have part of the technology to do it, but we don't have all of it. And robots interaction, as I was mentioning it today, is also a lot of like human-human interaction. And there is a lot of things. There are a lot of things that we don't know in human-human interactions. And that is also one maybe of the drawback and the problems we have now in robotics and that we are facing, and that's why we're trying to address right now the human understanding from the psychological, from the sociological point of view, and trying to reproduce, to model, to gather all this information, this data, and to try to find a way to have a global general model at the social level, but also at the individual level. Which might be different in the case of Jessica for like new fabrics and new materials, if I'm not wrong.
I'll just say some stuff. I'm apparently not really good at answering questions. One thing that I'm really interested in is that there are all these different disciplines which are exploring computation in completely different ways. So you have scientists like Mehrabian, who I mentioned at the Wyss Institute, who's really interested in coming up with theories that allow him to model things that he sees in nature, like the ruffling of a leaf. And he'll come up with a mathematical model, but only explore it so far to the point where he can describe something that's seen in nature and publish like a paper in Science about it or something like that. And then you have people in computer graphics who are developing all sorts of techniques that are very designed to be extremely fast and have these other interesting characteristics. And then you have us, like in architectural design, just like using this software that people made for us most of the time, not very powerful. And I'm interested in sort of what happens when we break down all these walls between these powerful computational models that are being developed and take those in our hands as designers and use them for not just modeling the natural world, not just making video games where you can kill things in highly realistic worlds, but thinking about how we can use them to design our world. So that's one thing I'm interested in. I don't know if that answers your question. I'm really also interested in advances in biology and sort of biological engineering. So if you think about all of us sort of as machines, essentially, we're living machines that transmit information in the form of DNA, and we're just starting to get to the point where we can understand any of that, and it's so like beyond anything that we have data for and can measure, because it's so hard to measure living things. But people are starting to think about, instead of just printing materials, what if we actually create real living biological systems? And that seems extremely fruitful for thinking about very powerful ways to really change everything. And those are the random things I'm going to say now.
There was a question waiting for a long time.
I just want to make a comment on your question. Actually, maybe in Gentiane's case, the promise was made not by her, but a lot of people before her, 50 years ago, when science fiction was written. And maybe, Jessica, you made your own promise, and you're not disappointing because you're answering your question. And you're trying to create a human intelligence or some kind of intelligence, and there, so it's very complex. So. Good luck.
Wait, there's a lot of questions, so let's take them in order. Did you have a, okay. So there's one here and then one there. Okay.
Yeah, just a specific one. When you said the edges growing created all that pretty form, was there any explanation on whether it actually helps with evolution or strength or fitness of that plant or anything, or creation?
I think that's, that's kind of a thing that people say. They're like, oh, things in nature are optimal, but really all they need to be is sort of stable solutions that can exist. So, I mean, whether or not that, for instance, the sea slug that I showed, they actually are basically one of my favorite animals. They harvest chloroplasts from algae. They store them in the ruffle on their back, and they use it as like a solar farm. It's called kleptomancy. That's really neat, right? So apparently they can use that ruffle to store lots of chloroplasts that they've harvested from algae. But I mean, whether or not a flat leaf, I think, could probably photosynthesize better than a ruffled leaf. Maybe there's some reason, but I think, the reason you see that shape everywhere is because that shape is very easy to make. All I need is one rule: grow more at the edge, and it makes that shape. So you see it popping up all over the place. And it's not a function of biology, it's a function essentially of physics.
Oh, sure.
Another question?
I guess it's actually a comment/mash note, which is, I just want to say, I love how I feel like the combination of the work you talked about, there's sort of great examples of using sort of data and science to get outside our puny little minds. And it's like sort of, there are these sort of invisible binoculars and new lenses that the universe has out there. And when you look at things like new ways of thinking in math or through nature, it's like you sort of take these things out of the invisible spaces where they were, and now you can put them on and look at things in a new way. So I think that's really cool about the work that you do.
Question, Felix? And I have one more after. I'm calling short tips.
Thank you for your great presentations. I have a question for Jessica. And in your presentation and your discourse, you seem to be very much interested in the idea of democratizing your production. And I was wondering if, apart from delivering the means for, general public to design your with your interfaces, if you have any idea or interest in actually unveiling a little bit more of what's happening behind, to, let's say, more the technical audience, like in forms of a patent or papers. Especially, some of your findings are really cutting edge, the folding systems and how to make a 4D printing. So that's kind of my question. Have you thought about that? Do you have any interest on going in that direction, or is more like generating the platform for final users?
We typically publish a lot on our website and our blog and our portfolio about how we implemented these systems. So we have a lot of details about, it's a rigid body physics simulation and how we had to simplify it in order to make it something simulatable and what went into that. We don't go as far as open sourcing all of our code. So I think, in some ways we describe very well the methods that we're using. And in the case we're referencing a certain researcher's work, we'll call out a specific paper, like it's Mehrabian's paper from this year it inspired this, and this thing by Eitan Greenspan, whatever it is. But as of yet, we haven't really open sourced much of our work. Part of it's because we're essentially two people, and we make very specific tools, which we then make money off of, so we can have a place to live and eat, those things. Which is not to say that I wouldn't eventually open source some things. We have some projects, some libraries, which are intended to be used by anyone, which we do publish on our site. But in general, we try to be very open about our methods and discuss all of that so people can make similar things without making things identical to ours by using the exact same algorithm.
Other comments? I just had one last comment before we break. Again, actually continuing on Felix's questions, and it might also be a question that you might all be interested to answer. It was this notion of accessibility, and the fact that you mentioned, for instance, that one of the main obstacles for accessing digital fabrication is the 3D design software that are seriously impairing most of the people I know, including myself, into sort of reaching to those technologies. I wonder if, and you were also kind of sort of grounding your research within the idea that it's ultimately for people to use, or you were talking about this intuitive understanding of the knowledge that sort of justified some of the approaches you were describing. So I'm just wondering, do you sort of want to specifically set up strategies for breaking that wall of knowledge obstacle?
Yes. Well, that's sort of what I was trying to get at, right? So we have, let's say, mass production. It was this new thing that happened, and suddenly, though, we had to invest a lot of money in some sort of tool, and then we're going to use that tool 1,000,000 times in order to recoup that cost. So maybe before your shoes were handmade by some guy and they fit you perfectly, they had that function of being for you, and maybe they made you happier because they're exactly what you wanted. Now you go to the store and you buy what is there because that's what you can afford to buy, that's what we had to make because of the limitations of mass production, and it might not fit you and it might not make you super happy, but those are the shoes you're going to get. So if part of the promise of digital fabrication is we can make anything, why not make exactly what we want? So both in terms of function, something that performs to your specifications, and in terms of what actually you like, that you enjoy. So then, yes, we're trying to make tools that let you do that, but the problem is how do you actually let people engage in the design process, and how do you get their input, and how do you do that without driving the prices up? So sure, you can still go to the handmade shoe guy and he'll make your shoes for $900, but most of us can't get $900 shoes.
Any thoughts on accessibility or intuition?
In the case of robots, accessibility is yet a big problem. There was this promise by SoftBank that they would sell a very cheap robot for less than $2,000 US, the one that I shown on one of my slides. But basically, they were completely out of scope when they were planning that, and they didn't even sell it, and they didn't even plan to sell it right now. We definitely need in our field a lot of accessibility, because yet now the robot is still something from the science fiction, and people are not used to it. And that's why also I was mentioning this problem of expectations that are too high. If people were like confronted with real robots, which was exactly the case when the personal computer started to happen, people knew their limitations, and people just accommodate with that. So if we could have super cheap robots that people can play around with, that would be of great help. And in terms of behavior modeling and these kind of things, it's just a software problem which can be very easily turned around, and that is not a very big problem. In terms of design, I have great expectations with the project I was mentioning, the metaphor robots and these kind of things, that using new design technologies, we can have personalized robots that at least respond in terms of like appearance and motion abilities to a certain number of person or personal preferences. And I'm thinking like Jessica, that like a few decades ago, everything was like custom made just for you, and now we have to do to mass production and to adjust to the product we're buying instead of having the product adjusting to us. And that would be great with robots, in particular interacting with us, that we could personalize them as much as possible and having really your own robot made just for you.
Thank you so much, all three of you. Can we give them another round of applause, please? So we're breaking for just 5 minutes just for you in time to get some coffee, and then we're getting to our third panel of the day on urban studies and big data. So it's also a very